Okay, so we're going to talk about how to do multivariate pattern analysis or multivoxel pattern analysis. So just a brief recap since it's been a while, but the last few months we've been talking about univariate analyses, and so those are often more deductive and more structural and more hypothesis driven. And today we're going to be talking about multivariate analysis or Mvpa. That's often more inductive or exploratory and more data driven. So Mvpa is a popular type of machine learning, and it often just relies on patterns and inferences without explicit instructions. So just a brief thing about machine learning in general. So a version that you might be familiar with is unlocking your phone with either your fingerprint or your face. And so when you set up your Face ID, then you're creating a database of pictures that your phone identifies as you, and then each time that you unlock it, if it is higher than a certain threshold of accuracy, then it lets you in. So it's testing your current face on the training set that you've already established. And more modern phones, if it's pretty confident that that's you, it'll add your current face into the existing database and it'll learn. So that way it can pick up if you're wearing more or less makeup or if you've grown a beard or something like that, it learns and adapts. So that type of learning and pattern recognition is similar to what we're going to be doing with brain data. So how does it work? So the point is to learn more about patterns in the data. So often traditional analyses are how your brain responds to certain stimuli, and this is almost the reverse. So based on the brain patterns, can you distinguish what you were looking at? So the types of, in univariate analysis, often what's returned as the result is different activation amounts, and this is going to be accuracy percentages of how accurate it was. So just a brief thing about what you can use. So in data science, popular languages or applications that you can use are to do machine learning or Mvpa are Python, MATLAB, or R, and we just use Python for this. So moving forward, I'm just going to be talking about the Python application for it. So just a brief recap. So for univariate analysis, you look at either a face or a house, and in a certain brain region, you get different activations. And is the difference in activation significant, yes or no? And with Mvpa, it's different. So in an area in the brain, you have different patterns, and based on the patterns, can you accurately classify or predict if you're looking at apples or oranges? And a popular type of Mvpa that I'm going to be talking about today is cross-validation. And in cross-validation, you are splitting your data into training and test sets. And so the way that you're going to create these training and test sets, you're going to split on different chunks or segments of the data. And what we did is each different person was a different chunk. And so that's going to be like a leave one out approach or leave one person out. And so when you leave one person out, you're training on everybody else's data except for that one person. So based on everyone's data, can you predict what the left one out person is looking at? And you're going to repeat this until every person has been tested on. So each iteration through this, for each person, you're going to get a performance score, an accuracy score, and then with your different groups, you can get an overall accuracy score. So let's start with an example with Hariri, which is one of the tasks that we do for our gender dysphoria study. So just a brief recap of this study, where people are going to be looking at either 3 faces or 3 shapes, like circles, and you'll have to say, does this face look more like the one on the left or the right? So this is going to be a block design, which we don't need to talk about too much, but just you'll see either all fearful faces or all angry faces or all shapes at a time. It'll never be a mix of the two, or a mix of the 3.
And just the purpose of the task matching is just to make sure people are paying attention to it.
Yeah. Right, so it's really to see the activation or the patterns when you're looking at fearful faces, angry faces, or a control circle. So this is part of our gender dysphoria study, so we're looking at differences in different groups who are receiving different hormones. And there's three that I'm going to talk about. There's the group that's receiving testosterone, the group that's receiving estradiol or estrogen, and the group that's not receiving any hormones. So briefly, just why I mentioned the block design is specifically for Mvpa, you're going to have more power, and so instead of in an event-related one where you just see an image and then it goes away and you see another one, this is for the whole block, like 25 or 30 seconds, you're going to see angry faces. So it's a bit less accurate, but it's more powerful, which is helpful for Mvpa when you get overall patterns. Okay, so step one, we're going to get some attributes, and we're going to see what time the faces or shapes appear on the screen, how long they're on the screen for. We'll set up some chunks and we'll set up some targets. So onset times and stim duration are pretty straightforward, and chunks and targets are a bit more confusing. And so this slide kind of breaks it down what these data sets are actually looking like. So the samples are going to be the activation values. The SA are going to be sample attributes, and so that's going to be your labels, your targets, and your chunks. So the targets, instead of having 3, we condensed it down to 2, either faces or shapes. So angry faces and fearful faces are the same in this example. So we'll have 2 targets, face shape, and then each chunk is going to be a separate person. So we'll have as many as in our sample. FA is feature attributes, and it's more voxel timing and position, so where and when in the brain things are happening. And then A is just data set attributes. It's more about like image headers and things like that. So this can be a little bit confusing, but I think especially that sample attribute is important and helpful. So taking a step back, we create just a text file that has our targets in one column and our chunks in another column. So each row is going to be 1 second. So for the first 21 seconds, they were looking at shapes, and this is going to be person 1. Then the next 3 seconds, there's this rest period where they're just looking at a fixation cross. It's more of a transition between stimuli. And then for the next 21 seconds, they're looking at faces. So that's pretty much all you need to set up these attributes, is the targets and the chunks. So next, we're going to pre-process some of the data, some of the neural data. So we'll just correct for motion, we'll get rid of some trends, and we'll z-score. So just a recap of what that means. So over time, there are these different trends in the data. These red lines are going to be different segments of a task. So often the tasks are split up into different runs. So that's what the red lines are, and you can see over time it starts to increase for each of them. So detrending just removes those trends, and then z-scoring drops it down to a 0 mean and creates a standard unit. So an increase in activation of 1 means the same thing at each voxel and for each person. So next, we're just going to lump some of our data into different groups, so based on our different hormone conditions. And we can add in different sample attributes, as many as we want. So we can add in a qualifier that they were receiving testosterone or estradiol. We can assign a label for the sex assigned at birth, and like our chunks, we can assign them a study ID or a different separator like that. So we made the groups based on hormones, and that's what we're going to be splitting our training and using for our training and test sets. You can use any of these. So we are going to do a leave one person out within each of those hormone groups. But you could have trained on all of the testosterone to look at different patterns in estradiol or anything like that. So next, how does cross-validation really work? And there are 4 main steps that go into it. There's the classifier, the partitioner, the error function, and the conditional attributes. So the classifier is the actual test. It's what gives you the accuracy score. And so we used a support vector machine, which is common in the Mvpa literature, and it reformats this multi-dimensional data into 2 dimensions, and it puts a line through the categories. It tries to separate it into the groups and make a prediction. So it looks something like that. And then you can see that it's not always going to be accurate. There's that blue dot that's on the green side. But it does its best to make to maximize the differences. So next is a partitioner, which is actually what's going to be making these different training and test sets. So those are some of the 3 more common ones, and we use the middle one where we're going to make different groups. And so within our testosterone data set, we have 18 people, so we need to make 18 data sets.
So the classifier, is it doing in each voxel? It does that, it creates that division?
Yes. Or within like a certain region, whatever you're using to mask it, yeah. So this is just the line that it looks like. So parts is my shorthand for number of partitions, so that would be 18. And we're splitting on the attribute person, which is just our chunks of each person. All right, so next, this one's pretty straightforward. Just by default, it gives you the misclassification rate and how many times it messed up. And often what's more easier to interpret is the accuracy score. So we're just going to reverse that and ask for it to tell us how accurate the model was. And next is conditional attributes. So by default, these are not enabled. But by asking for them, you can see how well it did on each stimuli. So it'll return this matrix, and you can see how often it got faces and shapes right and how often it got those wrongs. So without asking for this, you'll just see the overall accuracy score, but you won't be able to break it down and see where it was working correctly. So next, we'll look at some of the results. And so what do these accuracy scores look like in terms of the brain? So we looked at 2 different regions. One is the amygdala, the other is just the whole brain. So you get an accuracy score for each person in the data set. And so since we have 2 different conditions, we can have accuracy scores of either 0, 0.5, or 1. So 0, it didn't accurately classify either faces or shapes. 0.5, it got one of them correct in that person, and 1, it was able to distinguish between faces and shapes. So next, often what's more helpful is just to see a group mean. So we can take the mean of that, and we can see in our testosterone group, overall, it was 75% accurate. In our group with kids receiving no hormones, it was 56%, and estradiol is 50% accurate. So now that we're working with means and values for each person, it's starting to look more like data that's more familiar to everyone, so we can look at it in a more familiar way, like graphs. So this is just the visual representation of the group means. So on the Y is just the accuracy percentage in the different hormone groups. So we can see, just with the ANOVA, we can see that the testosterone group is significantly more accurate than the other 2 groups. But what does this mean? Is 50%, did it get all the faces right and none of the shapes? Is it a mix between the 2? So just based on the means, we can't look at that, but that's why we enabled those conditional attributes so we can see the breakdown. So this is the same axes and units, so it's accuracy on the Y, and orange is going to be how accurate it was in identifying shapes, and blue is how accurate it was in classifying faces. So overall, it was much more accurate with shapes, but with testosterone, it was much better with faces. So there's a couple different thoughts that we had about this, and one of them could just be sample size. Our testosterone group is a little bit bigger, but also just a way to interpret these accuracies, like what does it mean to be accurate on this? And so it's comparing the patterns of these shapes to the overall patterns. So just if it's more accurate in shapes, that means that the patterns are more consistent for all the shapes. And since we're combining angry faces and fear faces, that could be an option for why our face accuracy is lower, because different groups represent those two different emotions differently. But if that's the case, then testosterone would have similar patterns for both of those different emotions. And then if you map this back onto the brain, you can just see these are the areas of the amygdala that are involved with both classifying shapes and faces. So next, we did the same thing in the whole brain, and we can see that it's much more accurate. And we can add in the significant testing, and we can see that estradiol is significantly less accurate than the other two, and the other two are about the same. So again, what does this mean? Where are they performing better? And it looks like the shapes are about the same as before, but the faces are getting better, particularly in the no hormone group.
What does it mean that there's so much longer than there's a lot less, like significantly less of a chance? Right?
Oh, for faces?
Yeah.
Yeah.
They're getting it wrong.
Mm-hmm. Yeah, so part of that, it could be the sample size, but it also could be that there's two different faces in there, and it's trying to, if it's looking at, is this a face, is it a fearful face or an angry face, and it doesn't know, it could get, if the patterns are too similar, it's going to misclassify. So I think for within faces, 25% would be closer to chance just for the blue.
Yeah, I think one element in here that happens too, and why it's important to break it down by individual accuracy type, is essentially you can obtain 50% accuracy by always guessing shapes for everything.
Right, exactly.
So we can kind of see that if it was truly that, then all of estradiol, for example, here would be all shapes. So it is guessing faces sometimes, but I think a more even distribution of those two values, if it equally divides the accuracy, then that's more like the accuracy level that you would expect. So I think you're right in saying that 25% is below 25% for any category, whether it's faces or shapes, is probably chance.
And also, just regardless of the breakdown, just the fact that the model itself is way more accurate in the testosterone group, almost 100% accurate, and then is struggling to classify essentially in the brains of people who are receiving estradiol. That's interesting. Do we even have a hypothesis as to why that is? So basically, from what, if I'm interpreting this correctly, it means that the brain's response to faces and shapes is less distinguished. Like it's not distinguishing faces and shapes as much in the kids who are getting estradiol versus the kids who are getting testosterone nothing. The model's almost 100% accurate, right? So why do we?
So here's what I think based on this, because it seems like the shapes are always 50% and everything. So I think they're saying the default is shapes. Occasionally there's enough signal to say I think it's a face. And when that threshold is crossed, it's crossed a lot. Testosterone is usually correct, but in estradiol, it's not so much. They just do that. There's never enough. The machine is never confident enough to say it's a face, and so it always defaults to shapes. It's always right at the shapes, and it's missing a whole lot of it. I think that's the.
But I guess I mean why would it be the case in the estradiol group but not testosterone group? That whole pattern.
Because something about the signal is responding more consistently to faces than...
Or less consistency.
Less consistency.
Yeah, it could also be because of the two different kinds of faces that maybe, because it's looking at basically two different types of data and treating them as one.
No,
so
but
if
I'm
it's
more
saying,
concerned about the main effect here. Like, why is this different in the kids who are getting estradiol? Like, is there anything about these hormones that we think would be prompting the brain to respond differently to these stimuli? Like,
I think so. So there's...
There's a whole literature
on estradiol?
On testosterone. Not so much on estradiol, but testosterone.
Yeah.
Which
So I
says?
think the testosterone might be lumping both. So these threat-related emotions would be lumped together where they're seeing angry and fear as more similar, and so it's going to get it more accurate, whereas estradiol might see those as two separate emotions, and so if it's taking the mean of these two different patterns, it's going to be less accurate on classifying it. So I think,
might be explaining that.
yeah,
that whole
and I think accuracy could be improved if we split it up into not just face perception, shape perception, but emotion perception. So if you split it into those three groups, then I think accuracy could improve maybe in angry, and then you can see that fear is often, I think that breakdown would make more sense.
Yeah. It would be interesting if you then found at that point that estradiol's accuracy went up and testosterone's went down, because that would fit with that theory that they're less differentiated.
Interesting.
It may also just be we need
that's
more
kind of
people
what
and more
I'm
subject
thinking,
balance.
Like, is this a fluke, or is there like some sort of biological
Yeah.
hypothesis behind it?
I think we need more data to know. Yeah.
All right, cool. So taking out the none group, if we can make a different map and we put it back on the brain, so these areas in blue are going to be the areas that are more involved in classifying for estradiol, and the areas in yellow and orange are more involved with classifying for the testosterone group. So just you can see the regional differences that are involved. There's a lot of overlap, but these are the areas that are more important for classification.
And that's positive or negative.
Yeah.
So a signal in one area could be orange, but it could mean that every time there's a signal in that area, they're saying this is a shape, not a face, right?
Yeah. Cool. So I realized about partway through that I was going pretty quick, so we can have a brief recap. So when should we use Mvpa, and when should we use just regular analyses? So there's some pros and some cons. So one, Mvpa is data-driven, so there's no bias from any of us, but also it's data-driven, and so there's no guidance. And that can lead to a couple things, like we can see different areas are important that we weren't expecting, but that also means that it'll always find a solution, and so that means if there's a bit of skull that's still there, it'll classify it, or if it's something doesn't make sense at all, like logically, the model doesn't know that. It only knows what we tell it. So there's always going to be a need for us to manually verify the results and make sure that it makes sense, especially if you're combining some of this with survey data. If there's like an interaction that just doesn't make sense, it's going to find it in the data. Like we talked about earlier, it works best in block designs, which isn't always the most popular, most common way to do this type of imaging. But similar to the second pro, it can help identify these different differences that between groups that aren't apparent or don't show up in the univariate analyses. It's part of this is that it goes voxel by voxel instead of taking these group means, and so it can be more sensitive to different regional differences within an ROI. And it's not as common as the traditional ones, and so there's less gold standards. There's a couple different ways that are pretty common to do, and there's no really clear one best way to do it.
Can I add an example there on the last, on the pro side? This idea that you might not find the same result in a univariate design or traditional univariate design. One of the big examples in like our lab's work, for example, is the emotion-specific effects on activation of the brain. So differences between different emotions, like anger versus sad versus fear versus sadness. If you end up having many different emotional categories, sometimes your univariate analyses will not pull out emotion-specific differences as much. In the voice, for example, you wouldn't see areas that are responding differently to different spaces in a univariate approach. But if you were to do Mvpa and restrict your analysis to the speech perception areas, like Broca's areas, then you might see that your classifier is able to determine what the brain was hearing based on its response. So some of these more fine-grained differences between multiple categories or something that's better picked up by Mvpa than univariates. If you think about it, it's like a 5-level factor that's a lot harder to test for in a traditional ANOVA framework, but Mvpa can kind of help you get around those things.
It just to piggyback on that too a little bit is the it also, by using that same individual level data, each scan factors in, so part of the reason it can identify those differences is because it can be sensitive to individuals' contributions. So if as a whole most people are subtle, but you have a few people that have a pretty different activation pattern, it can pick up on those differences. But again, the disadvantage of that is it's also more sensitive to outliers in your data. So there's
Yeah, I
lots
think
of pros and cons.
especially for the people in this, doing this kind of research. One of the problems of comparisons is if you have differences in sort of variability within your group,
Yeah.
say patients or something, just that will automatically just reduce the ability of a group analysis on one group different than the other group. So we have to be really careful about that.
Yeah. And that is true, for sure. Yeah, like we see that in almost all our
It
data.
might be very good at it's predicting one individual subject and one individual subject's data, but taking that information and applying it to a different subject might be a different challenge in a patient population than in a typically developing healthy population.
All right, so that's pretty much it. I know that I went pretty quick, so here are some resources. So I know this is going to be either on the shared drive or passed around, so you can scan that. It'll take you to...
Or on YouTube.
You're right. You can scan it wherever. And there'll be a link to the documentation for the Python package that we used, a paper on cross-validation, and some of the other ways to look at voxel by voxel differences like Searchlight. And then there's a cool non-imaging tutorial that you can work with, which is this handwriting recognition data set. And similar to a brain picture, it's this picture of handwritten numbers and letters, and it goes pixel by pixel and tries to guess the accuracy of what's written. And that's it.
Yes.
So people are using this a little bit in clinical settings in situations where like you just don't know. Like you have people who respond to outcome, people who are through interventions, and people who don't respond to intervention. We're doing this with like epilepsy surgery. Going in, they have no idea who it's going to be. But so it's like there's no hypothesis, but there's a whole lot of data that maybe something can tell us something about that. So they're taking this and they're saying, okay, just is there any difference between this group that responded and this group that didn't respond in some sort of pre-baseline assessment?
Yeah.
So that's an area that is, I think, especially if you have no idea, to say, is there anything? Can this computer, the calculations and levels, we have no way of, our human brain can't do. The computers can do this sort of stuff now to give you at least some indication that, yeah, maybe there is something systematic here.
Yeah, and that's a point too where it's like the cost of accidentally getting a false positive is really low, but the advantage of getting a true positive is really high.
Yeah.
So if you're concerned enough to bring someone in for a brain scan and you have a training system that's maybe tuned to structural rather than functional images, you can just flag them and pay a little more attention and watch the case, and then you can respond earlier. And epilepsy is a great example of that, because the sooner you start the process of figuring out what's going wrong, starting treatments, it reduces the possibility of needing kind of extreme surgery. And if you can't prevent that, at least the accuracy of what the issue is. So I think that's really useful.
Yeah.
But you do have to be careful with it, right?
Yes.
It's
Yeah.
very easy to get results that are, because of the sort of the wild west of the statistics. It's
Yeah.
kind of
Yeah.
like,
Yeah, so going off of that and what Michelle was saying, since there's no real gold standard, it's often combined with other more traditional analyses, so it can help be more of explain findings. So paired together, it's really good.
Yeah. And in a few years, given how popular it is,
Yeah.
there will probably be some established testing. It's just these things take time.
Yeah.
I was told at SFM that univariate ANOVAs were the little leagues.
Little what?
Essentially, the little leagues, and Mvpa was where it's at. So some people really feel strongly about this being the next wave of fMRI analysis.
So are these the kind of things that that Google is doing to produce ads?
Yeah.
And,
Mhm.
okay.
Yep, absolutely.
Same sort of approach.
Yeah,
Absolutely. Anywhere where you have a big data
Yeah.
set, you can go on their job site. They're probably hiring 12 big data science people right now. So yeah, that's the kind of thing where you have a lot of data, and that's how, like, your example of the phones in the beginning, and your webcam that can put goofy
There was a
things.
thing where they had people draw certain images, and then once it had so many images, then you could tell you right away what that was.
Yeah.
So you'd say
Yep.
draw something, and you draw like a cat, and you'd be like cat, because it would compare to its database of things that had been labeled as cat.
Yeah.
Pretty cool.
So another example they do in Africa, there's this disease that's going through these plants that are really important, and so they've made this algorithm where you just take a picture of this leaf and it'll tell you if it's diseased or not. So just, again, with like surgery things, it's all this recognition with pictures could make all the difference, so it's pretty cool.
There was another thing like that in India with where they were going to rural areas and they just had their smartphone and they could use a
Yeah.
picture to identify, like, there was some eye issue or something, but the light could pick up the.
Essentially, it's a
the
bunch
issue.
of regressions. Like,
Yeah.
machine learning sounds really fancy, but it's just like a lot of
Yeah.
regressions.
Yeah. The singularity isn't happening anytime soon. Cool.
All right, thanks,
All
Colin.
right, cool.